Welcome to the next session of fundamentals of heat transfer. So we are going to start with module 2. And in module 2 we are going to discuss what exactly is a transient heat conduction. So far we have discussed whenever like whatever situation that we have taken for discussion, we always put an emphasis that it's a steady state. Steady state means temperature does not vary with time. So what exactly is transient heat conduction, and what are the scenarios in which transient heat conduction analysis will become relevant that we need to see, and what are the methods through which we can successfully do the analysis whenever the temperature is varying with respect to time. So transient heat conduction means variation of temperature with respect to time will not be equal to 0, which was the previous case for steady state. Now, let's say we have a metallic sphere, okay, and let's say the initial temperature of the metallic sphere is 100 degrees Celsius, and it is kept in an environment where the ambient temperature is 30 degrees Celsius. All right, and this is the initial temperature. So let's say we took out the metallic sphere out of a furnace and then we keep it in an environment. So after some time, has passed, the temperature of the metallic sphere will drop. At any instant, the temperature will drop. Now, this temperature, like if I measure it at this location, what is the temperature? Measure it at this location, what is the temperature? This location, what is the temperature? That means with respect to location, whether it is changing, that particular thing we need to take into consideration. Okay. So that means temperature will vary both with respect to location and also with respect to time. In case of a steady state, temperature was varying only with respect to location, okay, not with respect to time. So here it will vary even with respect to location and with respect to time. So when it comes to analysis of transient heat conduction, there are two very distinct cases. Actually, one is your lump system analysis. Okay, and the next one is either it's an infinite solid or it's an semi-infinite solid. All right. So what exactly is lump system? So let's say I have a sphere, same scenario everything. Which at time t equals to 0, its temperature is 70 degrees Celsius. So no matter where you measure, everywhere it's 70 degrees Celsius. Okay, no matter where you measure it. Then the same sphere, after some time, at time t equals to, let's say, 5 minutes has passed. No matter where I measure, the temperature is 30 degrees Celsius. So as you can see, as the time has passed, temperature has varied with respect to time. But temperature with respect to location is zero. That means no matter where you measure it, the temperature is same. Yes, it varies with time. At t equals to 1 second, there was a different temperature. T equals to 10 seconds, there was a different temperature. But at t equals to 10 seconds, no matter where I measure the temperature, everywhere the temperature is same. So in those kind of scenario, we consider it to be a lump system analysis. So under what conditions lump system analysis, like doing lump system analysis is actually easier compared to the other two part. And but you cannot use lump system analysis just for any situation. Lump system analysis can only be done under certain condition, and if those conditions are not met, then you have to either go with an infinite solid model or with a semi-infinite solid model. So let us see under what condition lump system analysis can be applied. So let's say I have a solid, and let's say the mass of the solid is m, let's say its volume is v, its density is rho, and initially at time t equals to 0, its temperature is Ti. Okay, and let's say it has a surface area As, and outside the heat transfer coefficient is H for the convection, and let's say the temperature outside ambient temperature is T infinity. In our scenario, let us say T infinity is greater than Ti. This means it's a heating situation. But don't get confused. Same expression can be used also for cooling situation. Okay. Then, as I said, again we have to see with respect to fundamental laws. So here, since we are dealing with solid, so continuity equation will not come into place. Here again, we are not dealing with any unbalanced force, so even Newton's law of cooling is, Newton's law of motion is satisfied. So only thing that we need to look into is the energy balance. So energy balance, simply we can do it as heat transfer into the body within a time dt. So let's say a small amount of time has passed. Within that particular time, what heat is coming inside the body should be equals to increase in temperature, increase in energy of the body within the same time interval dt. Isn't it? That makes sense, because heat is coming into the body, then definitely the energy of the body has to increase. So this is and since energy can neither be created nor be destroyed, both the quantities has to be equal. So how can I find how much energy has come? Since Newton's law of cooling deals with, because here we are dealing with convection on the outside surface, so we are going to use Newton's law of cooling, and this will be H into As, and since ambient temperature is higher, T infinity minus T. Why I have written T infinity minus T? Because after some time dt, the temperature of the body will change from Ti to an unknown temperature, a variable temperature T. And since this is in watts, okay, this entire thing is in watts. In order to find energy, you have to multiply it with the time interval, that is your dt. Okay. Similarly, on the other side, it will be from Cp delta T. We are going to take. Now, m is equals to rho into V, and this dt can be written as differentiation of T minus T infinity. You see here T infinity is constant. So if you differentiate this, this will become dt only. Alright, so these are the minor changes that we are going to apply here. Alright, and let's just rewrite this equation. So this will be h into as into T infinity minus T into dt will be equals to, instead of mass I will write rho into V into Cp into d into T minus T infinity. So instead of going for the next page, I will just erase this part and continue the derivation on the top. So if I just rearrange this after this part is starting here, if you just rearrange this, I can write d T minus T infinity divided by T minus T infinity will be equals to minus h, minus we have brought here because we have written, instead of T infinity minus T, we have written T minus T infinity, just to bring equality into the equation. As divided by rho V Cp into dt. Now let us integrate. This one I will integrate from initial temperature Ti to whatever temperature it will have after a certain time. And since H, As, rho, V, Cp all are constant, so they will just come out of the integration sign, and time will vary from 0 to t. Okay, so now if we integrate it, so this is basically dx by x. All right, so we can write it dx by x, integration is ln, so this will be ln t minus t infinity divided by ti minus t infinity. This will be minus h a rho v cp into t minus t infinity ti minus t infinity is equals to e to the power minus h a rho v cp into t. So as you can see here, temperature change will come exponentially, and it will keep on decreasing, and it will happen exponentially. Okay, now the thing that we need to notice is that if we have, let us draw a graph. All right, so the body starts with a temperature Ti, and it has to go all the way to a temperature T infinity, because then only the heat transfer will stop. Okay. And this will happen under certain condition. So if the exponent keeps on increasing, the curve will keep on changing like this. So this is b1, let's say, for a certain exponent. That is your if we rewrite the expression, t minus t infinity by ti minus t infinity is e to the power minus ha rho v cp into t. So this part I am representing as b. So if this is b1, and then after some time, if I change the value of v1 by changing any one of the property, I will get this b2, and sorry, it's just very difficult to draw, and this is b3. Okay, whereas b3 is greater than b2 is greater than b1. That means, and these are all with respect to time. So you see here, for this particular body which has an coefficient b1, is called as the response time, which has a coefficient p1, it will reach the T infinity temperature at time, let's say T1. This will reach at T2 and this will reach at T3. And clearly from this graph, we can see that T1 is greater than T2 is greater than T3. That means any body which has this particular curve will be more responsive with respect to the heat transfer. That means it will do the heat transfer faster. That means essentially, for lump system analysis to happen, we need HA by rho VCP to be as high as possible. Okay. Now, this can only happen if heat transfer coefficient is very high, surface area is very high, but volume is very low, specific heat is very low, and density is also very low. So that means in a scenario where we have very small body with a smaller volume but larger surface area, like a thin wire, can be considered as a lump system. But only by looking at an object, how can we say like this is just a thumb rule as an engineer? So we can clearly understand that the body which has to be suitable for lump system analysis cannot be having a large mass or large volume. All right, if it has a large volume, then definitely it will not be suitable for lump system analysis. So how can we ensure that we perfectly predict uh, what like which particular body can be used under lump system analysis? For that, we have a dimensionless number, just like Reynolds number. Just like Reynolds number tells you whether a flow is laminar or turbulent, similarly this dimensionless number, which is a Wyatt number denoted by Bi, and this is called as HLC by K. This Wyatt number has to be less than 0.1 for lump system to be applicable. Okay. Now, what exactly is Wyatt number? What is its physical significance? So this entire Wyatt number can be written as So I can just write it as H into delta T divided by K into LC, sorry, K into delta T K into delta T divided by LC. So you can clearly see it will go back to this previous expression what we have here. So what is this H delta T? This is convective heat transfer per unit area. And what is this K delta T by LC? This is nothing but your conduction heat transfer per unit area. So if convective heat transfer is less compared to conductive heat transfer, that means since we need a very low value, then those system can be considered to be Biot number. I mean like lump system analysis. Okay. What I'm trying to say is that let's say let's take this example. Okay, let us consider this as an island, and through to this island there are boats which are bringing supplies. All right, and these supplies has to be distributed equally all throughout this island. Okay, so they will drop the supplies here, and then island people they have to transfer it equally all throughout the island. Now imagine a situation where the people in the island are not very efficient. Okay, so these people distributing the supplies is a representation of your conduction, and this ship bringing the food or the supplies is a representation of your convection. This is happening within the island, this is happening outside the island. So this part is a representation of convection. Now for Biot number to be less than 0.1, I need higher conduction and lesser convection rate. Now let's say these people of this island, they are not very efficient in distributing the supplies, whereas the ships are very efficient in bringing the supplies. So heat is coming to the body from outside at a very fast rate, but inside the body, the heat is moving very slowly. As a result, what will happen? The temperature, the supply at this point will be different than supply at this point at any given time, which will not be satisfied with our lump system analysis, because in our lump system analysis, we said that the temperature at any location has to be same. With respect to time, it will change, but with respect to location, it has to remain same. So that means this will not be considered as a, this scenario will not be considered as a lump system. Whereas if you see, if these ships are not very efficient, whereas the people in living on the island are very efficient in distributing the supplies, then heat will move very easily inside the solid, whereas heat from outside will take a lot of time to come. That way, whatever supply is dropped on the island is manageable for the people if it happens at a lesser rate. So they will have enough time to distribute it equally all around the island. Okay, so this is just an analogy with respect to your lump system analysis. Okay. Now, if you want to find what is the heat transfer, so we just found out temperature distribution expression. Let us find out what is the heat transfer expression. So heat transfer is very simple. You just need to do apply, say same convection is equals to conduction through the solid, so it will be T, and this will be temperature at any particular time, since with respect to location it's not changing, it's a lump system analysis, and this will be T infinity. T minus T infinity. This will give you heat transfer, rate of heat transfer. Rate of heat transfer. All right. Now, what is the total amount of heat that got transferred? Okay. For that, you can use simply MCP delta T, but delta T has to be temperature at time equals to T minus Ti. I mean, it depends like whether Ti is greater than this or not. So this will give you your total amount of heat. All right, and what is the maximum? This is also equals to the our maximum is maximum amount of heat will be MCP, same thing we can use, and it's just has to be, see, maximum is when heat transfer is completely stopped. It means the body's initial temperature Ti has now become T infinity. So Ti minus T infinity. This will give you your maximum possible heat transfer. Okay. Now one last thing with respect to Biot number. Biot number is given by H LC by K. Remember, this is the K of the material. Okay, and H is for the ambient fluid. LC is called as your characteristic length. Okay, and LC can be easily found out by volume by surface area. So suppose you have a sphere. Okay, so for a sphere the volume is 4 by 3 pi r cube and surface area is 4 pi r square. So we end up getting r by 3 as the characteristic length. So this way, given depending upon what is the shape of the body, we can easily find the characteristic length. And H and K will essentially be given to you in a problem. So you can easily calculate the Biot number. And if it is comes less than 0.1, you can definitely go and apply the temperature distribution formula. T minus T infinity divided by Ti minus T infinity is equals to e to the power minus HAT by rho Cp V. And find out the temperature at any given time of the body. So this is about lump system analysis. Let's stop here and we will start the session again with respect to infinite solids and semi-infinite solids.